Hey Royals, this is problem number 2 of the universal law of gravitation. So what we'll do with this one is we'll look at the force of gravity of a 67 kilogram astronaut on the International Space Station. And then we do know that the space station is orbiting 385 kilometers above the Earth's surface. So drawing a little picture of what we have here, we have RE, the radius of Earth, and then we have the International Space Station. I'll just kind of draw as best as I can with this. What a space station would look like. So that's pretty good. We do have that the radius, we'll call that R, orbit. We know that our orbit is 385 kilograms, or kilometers, sorry about that. We do know the radius of Earth is, RE is 6.38 times 10 to the 6 meters. So this will be 3.85 times 10 to the 35 meters. So they're on the same order. So we should experience some decrease in the gravitational field intensity. So our total R would be RE plus our orbit, which would be 6.38 times 10 to the 6 meters plus 3.85 times 10 to the 5 meters for a grand total of 6.765 times 10 to the 6 meters. So we now know the radius at which the person is above, or this astronaut is above the center of Earth. Okay, so here we go. Let's write down what else we know. We know M1, we'll say 67 kilograms. M2 is going to be the mass of Earth, because that's what we're orbiting. So it's 5.98 times 10 to the 24 kilograms. And we're looking for FG. We have no idea what that is. And then we want to find out what little g is as well. All right, so starting in on this, let's go ahead and calculate Fg first. So Fg is equal to g m1 m2 divided by r squared, 6.67 times 10 to the negative 11. I'm just going to drop off my units for now, just to save some space here. I have 67 kilograms, and then I would have 5.98 times 10 to the 24 kilograms divided by that radius that we just found, 6.765 times 10 to the 6 meters. Oops, I'm not going to put units. I'm not going to put any units on any of them. If we calculate that out, we get that it's 583.937 newtons, or 5.8. How many sig figs do I have? 2, because of the mass. 5.8 times 10 to the 2 newtons. So we can now find little g. And so if we remember that the force of gravity is equal to the mass times little g, we do know what this force of gravity is. And we can use this to find out what little g would be as well. Or if you wanted, you could go ahead and you could calculate g using big G, m, e, and then divide by the radius squared above Earth. But because we're looking for little g, I do know what Fg is, and I do know what the mass of the astronaut is. So I can actually work this through, and I can say Fg divided by little m is equal to g, which is just simply the same thing as that equation there. So I get 583.937 newtons divided by the mass of the astronaut, 67 kilograms, is little g. And you can get an answer of 8.7 newtons per kilogram as little g. But that would just be simply g is equal to 8.7 meters per second squared. So you can see that the gravitational field intensity, in fact, has also decreased as well. So that's the answer to this problem. If you have any questions or anything, please let us know.